Good day, wonderful welcome. Here we can study about NMR spectroscopy and how to interpret the NMR spectroscopy results. The NMR can be used to identify carbon-hydrogen network of a molecule. Nuclei with an odd mass or odd atomic number have nuclear spin, could give NMR signal. We can see the carbon-13 and hydrogen-1 NMR. The cartoon represents the NMR spectroscopy. The overview of NMR is that the molecule is placed in the magnetic field. The molecule is treated with the radio wave pulse. Free induction decay can be created by the sample. The Fourier transform method convert the free induction decay into parts per million. Tetramethylsilane is used as internal standard. The signal from TMS defines 0 ppm on the chemical shift scale. Let us look at the principle of NMR. When the sample molecule is placed in the external magnetic field, the nuclei are aligned with the applied field. If it is aligned with same as the external magnetic field, it is called alpha spin state. It is lower energy state. And if they are aligned with opposite to applied field, it is called beta spin state. It is higher energy state. The energy difference between the two states depend on the magnetic field. If the external magnetic field is 1.41 Tesla, 60 MHz of radio wave pulse is used. If the external magnetic field is 7.04, the 300 MHz of radio wave pulse is used. The cartoon represents the magnetic field, and the nuclear spin state is indicated by the arrow. When the radio wave pulse delivered to the sample, the nuclei tips towards the Fleming right-hand rule where the receiver coil is placed. The rotation of the nuclear magnetic element causes the oscillating electrical signal. The nuclear magnetic element release the radio wave pulse leads to relax back the spin state. This causes the electrical signal decay. The electrical signal decay is called as free induction decay. The Fourier transform, which is a mathematical operation, leads to convert the signal of free induction decay frequency to parts per million. The graph plots against the intensity of the peak with chemical shift. The x-axis indicates the chemical shift in parts per million on delta scale. The carbon-13 NMR is between the 0 to 200 parts per million, which is called as chemical shift by their formula. The chemical shift range of carbon is presented here. It is very important to predict the number of peaks. The carbons that are having the chemically equal, it will give one peak. Let us see a couple of examples. 1,1-dibromoethane. It gives 2 carbon signal because both the carbon are not equivalent. The next sample is acetic acid. The acetic acid gives 2 signals because the presence of 2 distinct carbon. The carbon with sp3 hydrogen bond falls between 5 to 45 ppm. The carbon double bond with the oxygen falls on 160 to 210 ppm. Now, let us think about the hydrogen-1 NMR. For hydrogen-1 NMR, the chemical shift range from 0 ppm to 13 ppm. It is important to predict the distinct hydrogen environments are in the molecule. Each distinct hydrogen could give one signal. For example, the dimethyl ether gives only one signal because the hydrogen groups are equivalent. Another example. The 1,1-dibromoethane gives 2 signal because the hydrogen groups are independent hydrogen environment. Each signal can give many peaks because of the splitting and coupling with the energy level of neighbor non-equivalent hydrogen atoms within 2 to 3 bonds. The number of peaks can be estimated by the formula. The number of peaks equals to n+1. The n is number of vicinal and geminal non-equivalent hydrogen atoms. If n equals to 0, it gives single peak called singlet. If n equals to 1, it gives doublet. And if n equals to 2, it gives triplet peaks, and so on. If the peaks are more than 6, it is called multiplet. Example, the 1,1-dibromoethane gives 2 signals. One signal gives quartet peaks and the other signal gives doublet peaks. The peaks between their doublet is called coupling constant, which is indicated by J, and measured in frequency difference that is indicated in Hertz. The relative area under peaks can give common splitting pattern. For example, if the NMR signal is giving doublet peak, the relative area under the peak is 1:1. If a signal gives triplet peaks, the relative area under the peak is 1:2:1. If a signal gives quartet, the relative area under the peak is 1:3:3:1. The modern NMR can calculate and plot the value of relative area peaks, and it is indicated as arbitrary units. The shielding and deshielding. The electron cloud created by the circulating electron cannot shield the nuclei spin from their external magnet, which causes the signal falls in the downfield, and it is called as shielded. It leads to the chemical shift. Example, compare the CH3Cl and CH4. For CH3Cl, the proton is deshielded, it falls in downfield. The CH4 is shielded and it falls in upfield. The chemical shift table can be used to correlate chemical shifts with possible structural environments. The figure indicates the chemical shift of protons. It is important to remind not to confuse with the peak of solvent used to dissolve the sample. The dodechloroform used as a solvent for the sample. The dodechloroform solvent is only 99%, and the 1% of regular chloroform will give a peak at 7.2 ppm. Diastereotopic and enantiotopic hydrogen. If a molecule has diastereotopic hydrogen, it will give different signal. If the molecule has enantiotopic hydrogen, it is not distinguishable. It is good to use the z-test to identify the enantiotopic or diastereotopic hydrogen. We can see how to determine the carbon-hydrogen network of unknown molecule by NMR with their available information from MS and IR. Available information of MS and IR indicates here. The mass spectroscopy result indicates molecular weight about 46.1. The result from IR results indicates the presence of alcohol. Functional group. The molecular formula was calculated from the results of MS and IR. It is C2H6O. It is expected to be an ethyl alcohol. Let us look at the NMR results. Start with carbon NMR. The C13 NMR indicates the two independent carbon. In the proton NMR, there are three independent proton environments present in the ethyl alcohol. It is indicated by letters A, B, and C. The number peaks calculated by the formula for A is singlet. The number of peaks for B is triplet, and the number of peak for C is quartet. The NMR results indicate the carbon-hydrogen network is matching with the ethyl alcohol.